Hello, I'm Kentaro Yasu, a researcher at NTT Communication Science Laboratories. In this video, I'd like to introduce my latest research project called MagneSwift. MagneSwift is a very simple pin-based shape display that can present 2.5-dimensional shapes in response to hand-drawn input. Let me start with the background of this project. Pin-based shape-changing displays have been developed to present shapes, motion, and forces to provide embodied interactions and experiences. These studies are fascinating, and everyone would like to try the system. However, the barriers to purchasing, building, and operating such devices can be very high, because using many linear actuators to move dozens of pins inevitably increases the complexity and cost of the device. In contrast, as it uses magnetic forces to move the array of pins, MagneShape has a very simple configuration. The shape display consists of magnetic pins, an array housing, and magnetic rubber sheets underneath it. The magnetic rubber sheets can be magnetized instantly with neodymium magnets. And by moving the pin array on the magnetic rubber sheets, the magnetic repulsive force and the attractive force actuates the pins vertically. Therefore, MagneShape can display shapes and motion without any electronic components. However, MagneShape still leaves room for improvement in terms of interactivity. For example, when the user draws a magnetic pattern by hand on the magnetic rubber sheet, the pin array shows only a sparse arrangement of dots. This is due to the magnetic interference between the pins. There must be sufficient spacing between the magnetic pins, otherwise, the pins will repel or attract each other. To display shapes and characters globally, MagneShape requires an appropriate magnetic pattern and a time-consuming magnetization process. This compromises interactivity and limits the potential of the shape presentation using magnetic materials. Therefore, we developed a pin-based shape display that can be used interactively while maintaining simplicity in configuration. Here, I will explain the configuration of MagneSwift. MagneSwift consists of a high-density magnetic pin array mounted on a magnetic belt conveyor system. MagneSwift uses polystyrene foam for the body of the magnetic pins. In the previous study, the magnetic pins of MagneShape consisted of a plastic straw and a magnetic disc. Therefore, to avoid magnetic interference, sufficient space was required between the magnets, which reduced the spatial density of the pins. On the other hand, when the pin body is made of polystyrene foam, space can be gained by reducing the size of magnets, not by increasing the distance between the pins. This improves the spatial density of the pins. We measure the spacing required for different sizes of magnetic disks to avoid magnetic interference. As the distance between the two magnets increases, the upper disk, which has been lifted by the magnetic force, drops due to its own weight. At this point, the distance is recorded as the required spacing of the magnets. Based on the measurement results, we made a grid frame with a 1 mm thick acrylic sheet. The 6.3 mm pin pitch of the grid frame was designed to maintain the required spacing for the magnetic disks of 3.5 mm in diameter. However, since there are up to 8 other pins around each pin in the actual pin array, we made 25 pins and moved them up and down to verify that the magnetic pins do not cause magnetic interference in the actual pin array. The results show that for the magnetic pins with 3.5 mm magnetic disks, 2 or 3 pins would remain floating due to magnetic interference. Therefore, we switched to using 3 mm diameter magnetic disks for the magnetic pins. In addition, we rotated the grid frame by 45 degrees to reduce the effective pitch between the rows of pins, and achieved a high-density magnetic pin array. The next part explains how to operate the magnetic pin array. This is a magnetic belt conveyor system. We purchased a small belt conveyor and replaced the supplied belt with a magnetic sheet. On the top of the system, a magnetic drawing window is mounted. Since a magnetic viewing film is attached in the window, when the user draws magnetic patterns using a neodymium magnet, the drawn magnetic patterns can be seen. When a magnetic pattern is conveyed under the high-density pin array, the shape appears on the pin array. Then the magnetic pattern will be reset by a magnetic eraser, which is a 100 mm wide neodymium magnet. Using this system, we investigated the appropriate size of neodymium magnets for drawing magnetic patterns. We prepared a neodymium magnet with diameters of 2, 3, 4, 6, 8, and 13 mm and draw a circle with a diameter of 15 mm on the magnetic sheet. As a result, when neodymium magnets with a diameter of less than 4 mm were used, some of the displayed shape tended to be lost. On the other hand, when a magnetic pattern was drawn with a 13 mm diameter magnet, there was a significant variation in the levitation height of the pins. In contrast, when the magnetic patterns were drawn with 6 mm and 8 mm diameter neodymium magnets, a firm circular shape was displayed with no missing parts. We also investigated the optimal speed of the conveyor belt. By measuring the dynamic levitation height of the magnetic pins at different conveyor belt speeds, it was found that the dynamic pin levitation height was consistently higher when the conveyor belt was moved at 80 to 90 mm per second. Thus, by integrating the high-density magnetic pin array, appropriate magnetizing magnets, and the magnetic belt conveyor system, we have achieved a pin-based shape display that can present the shapes of hand-drawn magnetic patterns. Based on the system, we have made several application examples. This shape display can present shapes without any electronic components. By rotating the conveyor belt back and forth with a hand crank, the user can quickly modify the magnetic pattern multiple times using an eraser tool, a strap tool, and a magnetizing stylus. MagneSwift can also be used as an interactive storytelling tool. By controlling the movement of the pins, it can move lightweight objects such as a toy car and paper dolls placed on the pin array. We have also implemented games where hand-drawn shapes present physical actions. In the shooting game, the player manipulates the pins to knock down alien figures placed on the pin array. And in the ball-carrying game, the player carries a ball to the goal while avoiding obstacles. These games can be further enhanced by adding sensors and actuators to the system. For example, if a sensor module detects that the ball reaches the goal within the time limit, the monitor will show that the player has won. However, if the sensor does not detect the ball within the time limit, the monitor will show that the player has lost. This suggests that passive materials and digital technology can facilitate interactivity with lower power consumption. Finally, the remaining challenges. First, the limitation of shape presentation. Magnetic flux is concentrated with a finer magnetic pattern. Therefore, MagneSwift is good at displaying fine lines, but not good at displaying a large solid shape. When a large magnetic pole is drawn by hand, the magnetic flux is concentrated only in the periphery. To display large solid shapes, a magnetic strap tool can be used. However, it is still a bit difficult to display undulating terrain. Second, the tilt angle. In the ball-carrying game, the pin array is tilted slightly so that the balls placed on the pin array will roll down unless the player draws a shape. Tilting the pin array up to 25 degrees has almost no effect on the behavior of the pins. However, this pin array cannot be used by hanging it on the wall. Third, cost. The material cost for the magnetic pin array is only about $2. However, the conveyor belt we purchased cost about $430. To reduce this cost, we could consider using commercially available robotic modules or kinetic toys instead. Meanwhile, the interactivity of MagneSwift can be enhanced by combining digital technology. For example, it is possible to use projector to add colors to the shapes displayed. Also, if a magnetic reader and writer were attached to the system, it would be possible to capture, transmit, and reproduce magnetic patterns. This would allow users to send shapes to remote locations. That's it. Thank you for watching.